Welcome to video lesson number 1. Today's topic will be accuracy, precision, and percent error. We're going to begin our discussion with the meaning of accuracy and precision, and we're going to illustrate that with the analogy of a dartboard. As we look at the dartboards projected on the screen, we notice with the first dartboard, the X's represent where the darts landed. And this is probably the result that I would get if I was throwing darts. The X's are nowhere near the bullseye. Okay, we're trying to aim for the center here. And you can see that they're just sort of scattered about randomly. So in describing the results of these darts being thrown, we would say that Mrs. Lewis is not very accurate. Okay, ideally, we want to hit the bullseye. I am nowhere near the bullseye. Okay, so we would call this result not accurate. All right, in further evaluating these dart throws, we talked about how they're nowhere near each other. I couldn't reproducibly land the dart in the same place. And so that indicates that there's a lack of precision in my dart throwing. All right, there's no matter how many times I threw it, they kind of just went all over the place. No pattern, and it's sort of a random cluster, a random organization. So we would call this data also not precise. Okay. Probably not a good result if we're playing in some kind of dart game. You wouldn't want me on your team, this person. All right, as we look at the next dartboard, we see again that we have no X's in the center. So by the same logic as the previous example, we would say that this is not accurate. No bullseyes, right? But what's different in this one is that all of the dart throws, all of the X's are clustered in one space, which means that someone was reproducibly able to get this result. So that demonstrates a precision to the data. Okay, so though this data is not accurate, it's not hitting the bullseye, it is precise. Okay, the next dartboard. Now, in this one, we can see that the 5 attempts have all different locations. One of them is a bullseye, and the other 4 are sort of evenly spaced around the bullseye. So if you think about if we were to sort of average this data, average the location of the darts, we would note that that average would lie right here near our center bullseye. So even though this data is not all in the center, it's still pretty accurate because the average of the data, the average location of the dart, okay, would essentially be right here in our bullseye. So we would consider this data accurate, but it is not precise, right? Because the different darts have all landed in different areas. Okay, so we would label this accurate, but not precise. Sorry about my handwriting, getting used to this new pen. All right, and then our final set of data. Wow, this person was a ringer. They hit all 5 bullseyes. So obviously, this was a very accurate dart thrower and also very precise, could reliably make that bullseye, okay? So this is our last example of accuracy and precision. And so these descriptions of the pictures that we're seeing are qualitative descriptions. So we'll say, oh, this data is accurate but not precise, or this data is more precise than another set of data. So these are good qualitative terms to use when we're discussing data, okay, and darts for that matter. But in chemistry, we're also interested in a quantitative representation of accuracy and precision, in fact. And so we're going to move on now to the idea of percent error. So as you can read the text on the screen, each measurement is a comparison of a physical quantity with a standard unit of measurement. The accuracy of a measurement refers to how close the measurement is to the true or correct value for the quantity. So percent error is a measure of accuracy. And you'll see in just a moment that it's a numerical representation, that it's a quantity that we can discuss. So in the lab, we're going to make lots of measurements, and you already have started to do this in your measurement lab. So we want to make our measurements as accurately as possible. And so sometimes if we end up with an experimental value, we want to know how close we are to what the true or literature value is. What did we expect to get, and what did we get for an answer? So we have a formula for calculating that, and this is called the percent error formula, and it's given here in words. Okay, the percent error is equal to the observed value. What did you see in the lab? What did you record? Minus the true value. What value can you look up in a textbook or on the internet and compare our value to? And then we divide that by that difference by the true value and multiply by 100 to get our percent error. Okay, so I just like to make a note right here that the observed value is what you get in the lab. What did you record? Okay, the true value is what does the book say you should get? And by book, I mean any reference. It could be the internet, or it could be a book. All right, so we're going to look at a mathematical example of this. And you're going to use, when you do this calculation, you're going to use everything that you know about calculations in science and now sig figs. Okay, so suppose, for example, we find the melting point of a substance to be 198 degrees Celsius. The true value from the textbook is 200 degrees Celsius. So we would proceed to use the formula for percent error. Now, for problem solving in chemistry, we have an expectation that you're going to do this in multiple steps. Okay, so first thing you do is you write the formula that you're using. So percent error equals observed minus true divided by true, sorry for my text again, times 100. Okay. We have a cat passing through here. So that's observed value, 198 degrees is what we observed in the lab. The true value is 200 degrees. And then the true value goes in the denominator as well. Now, percent error, so we do this calculation and we come up with negative 1.0%. So I will talk to you about the process that we go through to get to that number in just a minute. But I want you to notice the following things. Percent error can be a negative number, okay? Do you see that I am not asking you to take the absolute value of your answer? I want you to keep the negative number there. What does the negative number tell us? It means our answer was too low. What would a positive number tell us? That our answer is too high. So that's what this means by this informs your error analysis. We include units with the measurements. You can see I have degrees Celsius there. But when we get to our final answer, of course, the unit is a percentage. Okay, so all of that drops out when we do the calculation. And the kicker here, the challenging part where people sometimes make a mistake is that percent error involves both rules for calculating sig figs. All right, and what I mean by that is we're going to use our addition and subtraction rule, and then we're also going to use our multiplication and division rule, and we're going to do it stepwise. All right, so let's just recall. The rule for addition and subtraction is to basically line up your numbers that you're adding or subtracting, do the calculation, and then you're going to round to the least precise place value. Okay, so by that, and when we take these three numbers and add them together, 9.62, that 2 in the hundredths place, is the least precise of the data we're working with. So when we get our answer down here on our calculator, we have to round to the hundredths place. So we are going to have to use this rule when we use the percent error formula. Okay, so if I go back and I look at the calculation that we're going to do here, so 198.0 minus 200.0, okay, if you do that in your head or on the calculator, you're going to get an answer of negative 2.0. Okay, so I took the 10th place here and the 10th place here, and so my answer here goes to the 10th place. All right, that is my numerator. And then my denominator is just 200. I haven't done anything with the denominator yet. All right, so that's your order of operations from math, right? You have to do this subtraction problem before you're allowed to do the division problem. So when we're dealing with sig figs, we have to use the subtraction sig fig rule before we divide. All right, so then if we do this problem on the calculator, negative 2.0 divided by 200, we get the answer, which is given here already, negative 1.0%. All right, so we had 2 sig figs in our numerator, 4 sig figs in our denominator, so our answer has to have 2 sig figs. So that is an example of our second rule for calculating with sig figs. When you divide, the calculated answer contains the same number of sig figs as the measurement with the least number of sig figs. All right, and so we just saw that in the example that we did. Here's another example here. Our numerator has 6 sig figs. Our denominator has 3. We do the math on our calculator, but don't write it down because we know our final answer can only have 3 sig figs. And so that's what we round to. Okay, so there's a little quick review of sig fig rules in doing calculations. And we've applied that now to doing a percent error calculation. All right, let's do one more percent error problem together. We'll set it up from start to finish. The literature value of the atomic mass of an isotope of nickel is 57.922. Okay, we don't really know what any of that means yet. It's sort of just a lot of gibberish. We're going to learn about it soon enough in chemistry. But what I want you to pay attention to is the literature value. Okay, so that means when I use my formula later, that's my true value, literature. Okay, in a lab, if a lab experimenter, okay, so here's some key words, lab and experimenter, determined the mass to be 59.6, so they observed 59.6. What is the percent error? Okay, so to do this problem thoroughly and completely and to get full credit on a test or an assessment, we start by writing the equation, the formula for percent error, without any numbers in it. Okay, so this is just what we're going to substitute into the equation. So percent error equals observed minus true over true times 100. And then we're ready to start putting the numbers in. Now I'm going to leave units out of this calculation because I know at the end it's just going to be a percentage anyway. And I feel like the units will muddy up the problem a little bit. Okay, so we know what units, they match each other, grams over moles, whatever that means, okay? And then we're just going to substitute the numbers in. So our observed value, 59.6 minus our true value, 57.922 over 57.922 times 100. Okay, now before you go crazy with the calculator, we have to show some restraint here. We're going to do this in 2 steps. Okay, why are we going to do it in 2 steps? We need to subtract first, do sig figs, then we divide, and we do sig figs again. Okay, so we're going to use both rules. All right, so on your calculator, if you subtract these 2 numbers, we should get, I have, check this for me, 1.7 grams per mole. Okay, 1.7 grams per mole. Now, that might not be what you got when you typed it into your calculator, but because you're using the subtraction rule and this number goes to the tenths place, this number goes to the thousandths place, we have to round to the least precise decimal place, which is the tenths place. Okay, so 1.7 is what we round to. And that's going to be over our value for our true value, 57.922 times 100. Okay, so this was our first time we used sig figs, was after the subtraction. And we applied the subtraction rule. Now we're going to divide. So again, plug it right into your calculator. Everyone's good at this part of it. Okay. And before we write down an answer, we recognize there are 2 sig figs in our numerator. There are 5 in our denominator. So we can have 2 in our final answer. Okay, that's the sig fig rule for dividing. Which number has the fewest number of sig figs? Okay, it's always going to be the numerator probably. And so in this case, there are 2 sig figs here. So when I take my number off my calculator and round to 2 sig figs, I get 2.9% error. Okay, then you get to the end of this problem and you ask yourself, does that make sense? Should my percent error be positive? Is my observed value too high? Yes, it is. Okay, so the sign of the percent error makes sense. Does the magnitude of the percent error make sense? Oh, about 3% error? Yeah, that seems right. 59.6 isn't that far off from 57.922. So anytime you're doing a calculation in chemistry, I do ask you to think about, is that number seem too big, too small, negative, positive? Does that make sense? Okay, and then that will allow you to think about not just going through these steps and completing them, but just if your work is making sense and if you're understanding the concepts behind what you're doing. Okay, so now you are all set to do some extra practice with percent error. Please ask questions in class and check your work as you go. And we will discuss this again when we talk about the measurement lab later this week. Thank you.